Hello, this is group 14, and this is our checkpoint 3. So for the assumption of constant linearity, as from this graph with our residuals versus fitted, with the model with total crimes based on percent population under poverty, percent unemployed, Lamasse percent police on patrol, and percent not high school grad, you can see a slight downward curvature in the data, but the assumption of linearity is not violated as it is fairly linear and we can continue with the model. Breaking it apart by variable, with all other variables in the model controlled. On the top left here, you can see percent population under poverty, which is fairly linear and looks pretty well distributed around the regression line. The one on the top right, percent unemployed, with all others controlled, you can see it's still linear. You don't see a pattern in the data, though it is fairly clustered. Bottom left here, it's very heavily clustered, but we don't see any patterns in the data. And again, on the bottom right, percent not high school grad, you can still see a cluster, but it's no clear patterns within the data.
Looking for constant variance, you can see as our fit in this scale location graph, as our fitted values increase, or the magnitude of our standardized residuals increase. As you can see with this line, that's increasing. We did a Booch-Kagan test, and our p-value as well, which suggests that we have heteroscedasticity.
The next assumption that we looked at was normality of errors. So here's a histogram for the residuals for our fitted model. And we can see that it has slightly heavy right side. And if we look at our next model, or go back, we can see the QQ plot. And this is supported here where this, all the points should be following the line closely. Here at the end, they tend upwards, which means that we are getting not normal residuals. And that is supported by the Shapiro-Wilk normality test that we did, because we have a exceptionally low p-value, suggesting that we can reject the null hypothesis and state that the errors are not normal.
Next, we have the outliers and influential points. So we performed a Cook's distance test, and from looking at the plot, most of the points are clustered around the middle line, and our significance level is around 0.5, but we notice that all the points are within that range. Even though some tend to have an influence on the line, they don't exceed that range, so we are okay to identify that there are no outliers or significantly influential points. Now we're going to analyze the total crimes based on a continuous variable and the poverty tiers. There were 3 poverty tiers split across the levels of low, medium, and high, and our continuous variable is percent unemployed. So from looking at this model, we see that the intercept of total crimes at a low poverty level when percent unemployed is held to 0 is 4,927 crimes. With each percent increase in percent unemployed, it results in a 127.4 increase in total crimes, but this value was not significant, so it doesn't explain as much. Next, when we look at the categorical variables of poverty tiers, medium and high, they increase the intercept by 4,775 and 4,992 respectively, and these values were significant, indicating that the total number of crimes would increase based on the different poverty tiers. Along with that, looking at the impact of the poverty tiers on percent unemployed, for medium and high, they result in negative 285 and negative 104 respectively, meaning that if the poverty tier changed, percent unemployed would actually decrease and would result in a decrease in the number of total crimes, but both these values were not significant, so it can't be explained as much. And also noticing the sign reversal could explain some multicollinearity and could not be treated as significant. So along with that, we have a R-squared value of 0.378, which means that the variability in total crimes can be explained at 37.8% by these variables. And this is our model for identifying total crimes by a continuous variable in the poverty tiers.
So to summarize, the assumption of linearity, while the distribution isn't perfect, there isn't clearly another model that would be better. and the added variable plots also show no clear patterns.
Along with that, the other assumption that was held was the outliers. Using Cook's distance tests, we found that we have no data points with a Cook's distance greater than 0.5. This means that none of our outliers are highly influential.
As you can see with the Pagan test, the p-value was low, which suggests that we have heteroscedasticity. This is supported by the graph of the scale location plot, which shows that the size of the residuals increase as the fitted values increase.
Another violated assumption is the normality of errors. As we can see, the p-value for the Shapiro test is very low, so we do have a error normality problem, and this is supported by the smooth curve shape of the QQ plots. Thank you for listening to our presentation.